start. Hi, I'm Julia Kasmire. I'm leading the session today on data pre-processing. My teammates are in the chat, so they will be able to answer some questions in the chat if you want. We are recording this, so it will be posted later on our YouTube channel for those who want to review the contents of the presentation. Just want to say happy May the 4th, everybody. And just to make sure that everything is working appropriately, I will start with a Mentimeter poll. So if you go to menti.com and use the code 59140979, that code should be written at the top of the screen. So the poll is just, can you hear me? So let me know. It looks like everyone can hear me. This illustrates not only to double check that everyone can hear me, which is an important part of a presentation, but also it gives you an opportunity to log into Mentimeter. There are several interactions throughout this workshop that allow you to give short answers or vote in polls and different things on Mentimeter. So this is just another way to increase interaction in the workshop and also get some feedback from you throughout the event. There's also some question and answer slides and some opportunities for you to ask questions and give feedback to me. So let's move forward. We don't necessarily need to wait for everyone in the workshop to answer this poll. Although please do, if you have not yet answered, go to menti.com and use the code at the top of the screen. Okay, so today we are talking about pre-processing, and that starts with what is pre-processing. And then we also talk about some of the more specific topics within pre-processing, such as integration, cleaning, reduction, and transformation. Following a short break, we will move to a live demonstration of some code that you can find online. And there'll be lots of opportunity, especially during that live demonstration, for question and answers and a bit of interaction. So to start off with, what is data pre-processing? What is this all about? Why are we even here today? Importantly, data pre-processing, also known as data preparation, is an important part of any data analytics project. It's the sort of early steps of turning raw data into analysis-ready data. So lots of people, if you've gone through sort of data studies in formal education, you know, maybe an undergrad or a master's degree or modules or something like that, you'll have been given analysis-ready data to work with. And that's very different to work with analysis-ready data and do the actual statistics or an analytic sort of processes. It's very different when you get raw data from messy sources, maybe scraped from the internet or from some different kinds of sensors or things that are a bit like unreliable. And most data pre-processing includes some or all of the steps, not necessarily in this order, of integration, description, summarization, visualization, cleaning, reduction, transformation, discretization, generalization, anonymization, and potentially much more. So, okay. And it's important to know that your particular process that you follow from turning your raw data into an analysis-ready data for your analysis may use some or all of these steps in different orders. There's no exact right or wrong way to go through it. It depends on what your data looks like to begin with and what you want it to look like at the other end. So let's just take a moment. When this slide was prepared, which I think was 2001, there were 500 million tweets being sent every day. There was 28, I think, petabytes, I could be wrong about what that stands for, generated in daily, I think, in 2020. You know, there's all these huge volumes of data being generated every single day. And working in data, it's described as by people who describe working in data as the sexiest job in the 21st century. And that's probably a bit of an exaggeration, but it is an important job, and it is an incredibly useful kind of job to be good at, because it's only increasing in popularity. It's only becoming more important because the volume and complexity of data is increasing. But it's not just the total volume of data that matters. You have to get insights out of it, which means you don't just want an overwhelming stream of stuff. You want to get the value, you want the relationships, you want the understanding that comes with being able to sort through vast volumes of data quickly. And an important concept here is the garbage in, garbage out principle, which is that raw data is like a heap of household waste. There's lots of potentially valuable things in there. They're at least valuable for some people some of the time, but you don't get as much value if you just take it all in one big heap. What you want is to sort, grade, clean, identify, sort of maybe repackage some of the data. That's where the real value comes from, pulling out a certain kind of data from the heap and, dealing with it separately. And that's what data pre-processing is about. So here's a poll, just really quickly. Get an early sense of your time, like how much of your data working time is spent on acquisition, pre-processing, analysis, visualization, or other. So this, you can do these, this is a sort of ranking. Okay, so we're getting a lot of time spent, our early respondents, on analysis is popular. Acquisition is another popular one. Let's see, we'll get some more participants. Oh, pre-processing coming in hot. Okay, good. Acquisition, it seems, is not as important. Oh, no, it's climbed into third. Okay, good. This is an interesting one. Probably we're not necessarily very aware of how much time we're spending on this, or exactly where the boundaries are between pre-processing and analysis, for example. And that's fine. This is just first impressions. What do you think off the top of your head is what occupies most of your time? Okay, so it looks like pre-processing and analysis are our top, first and second. And that makes sense because some studies done by Forbes found that data preparation accounts for about 80% of the work of data scientists. And analysis is also up there, it's popular too, but specifically 19% of their time is on collecting data and 69% is on cleaning and organizing data. So cleaning and organizing sounds like a really boring part of the data preparation, but it's hugely important in terms of the volume and time spent on data, which is why we're having this session today, because it's easy to overlook data pre-processing, but it turns out to be hugely important. So collecting data, we'll cover just really briefly. You can, of course, generate your own data. You can scrape data from websites using APIs. You can get third-party platforms, lots of other things. You can download data from them. You can capture actions from automated processes, like you can output the log from a GitHub repository or something that registers when people make commits. There's lots of other sources for getting your data. These are just some of the ways. And it's important to think about when you make your data, or get your data, you have to think about what shape it comes in, what volume it comes in, whether it has everything you need or whether you have to combine data sets. And these things tend to be a little bit harder to work with than data that's given to you ready for analysis in a class or as part of a sort of assignment. So when you get your data from the various sources that you get it, you do always want to check it. And there's two main ways to check data. There are, of course, lots of other ways, but I only want to talk about two. The first is the metadata. So this is kind of the documentation that comes with data. And that is data about data. So you want to do this to understand what's available, what's contained in it, what format is it in, what type of data is it, its volume, its complexity, things like that. There's also exploratory data analysis, which is analyzing data sets to summarize their main characteristics, often with visual methods. So you're probably very familiar with these both, but you may not know that they are ways necessarily that they are ways of checking your data. So let's say, for example, you have some sales data and you want to build a model to predict the performance of the next month. Metadata is probably not as useful in this case because sales data is probably something that you're generating in-house if you're a company that has, or a business that has some sales data. So exploratory data analysis in this case, you probably want to check, what trends are going on, things like that. But there are other cases in which different kinds of checking is more appropriate. So let's just have another quick interaction on Mentimeter. So when you, depending on the kind of data that you get, different methods will be more appropriate. So just let me know, how do you check your data? Exploratory analysis and documentation coming out on top early days. Lots of people might just, eyeball it. They just look a bit at it. I mean, that might work depending on the volume of your data. That might be fine. So far, no one has admitted to not checking their data, which is positive. Exploratory analysis looks like the most popular. And, this makes a lot of sense. We want to know the mean and standard deviation for different columns, for example, how many rows are in this data, things like that. This is basic stuff. We're all pretty familiar with it. I am interested to know that eyeballing it is the second most popular. It's great. I love the interactions on Mentimeter because they're anonymous. You can just respond. It's great. I love the honesty. Okay. So that's just a little bit about data pre-processing as a big concept. Now onto the first main topic contained within data pre-processing, which is integration. Data integration is about combining data from multiple sources, and it can be done to improve the quality of the data, to enrich the content, the data with additional information, or to allow reliable data analytics. And there are more reasons, but these are the main reasons. Broadly, integration is about joining. Now, you might be familiar with join tables and things like that. And the right way to join depends on what question you're trying to answer by joining these tables, these data sets, and what the data sets look like. So there are 4 here: inner, full, left, and right, and we'll cover these in more detail. So an inner join is the intersection of 2 tables. So this is usually considered the default join or the most basic join, and it returns the contents of both tables only when they match. So in this case, all of the resulting output table only has 3 rows because there was only 3 rows in these input tables that match, and there are no gaps. There's no empty columns. An outer join is the combination of both full tables, leaving gaps where there is a mismatch between what the first and second table. Okay, this makes sense. This is like the union of the 2 tables. So inner, outer, great. Now it comes to left and right. So in this case, a left join includes all rows from the left table and the contents of the right table only if they match with something in the left table. So you'll see there's an empty gap here. Something was carried over from the left table wasn't included in the right. And it's important to notice with left join and right join, which is the exact reverse, that it's sensitive to order. So you have to be careful about which table you put first or in second, depending on which table you want to keep the whole of. So because they're sensitive, you do have to think a little bit more carefully, whereas the inner and outer joins, because they're not sensitive to order, they give you a more reliable result. Now, when you're joining tables, you have to think about, how similar are the two tables that you're joining? Are they, I mean, there's lots of things to consider. Generally, we'll probably be working with something. You may have to convert, for example, a table from Excel into CSV so that you can then merge it with another table that's in CSV. So that's something you have to think about. That's also part of pre-processing. But you also want to make sure that they are maybe in the same orientation, that they use the same units, that they have the same sort of structure and identification, so things like you have to consider whether a person's name is in its common format or its full format, things like that, whether they're listed as Clinton, Bill or Bill Clinton. You have to think about these things. And that's something you have to do even before you join the tables. You have to explore and check the data in both tables a bit carefully with the view that you're going to join them. So that's something to consider. Now let's look at an example. So health surveillance. Data from many different sources needs to be collected, including like travel and information, immigration records, for example, doctors, emergency hospital admissions, things like that. If your goal is preventing the outbreak of epidemics that requires monitoring of occurrences of unusual patterns in real time, for example, if there's a global pandemic predicted on the horizon, you might need to collect and join lots of data from lots of different kinds of records, and you're not going to be able to force those sources of data to be in a uniform format or order or structure or orientation. Obviously, another concern with joining these kinds of things is privacy and confidentiality. If the data, especially after it's been joined, is stored in some kind of accessible way, you have to make sure that it's carefully anonymized or protected or encrypted. But even if it's just being stored on your computer, you have to make sure that you are using the information correctly. So you have to get sort of like your data management plan checked to make sure that you're storing it properly. That's just something to consider when you're joining certain kinds of records that have protected data. Now, beyond purely joining tables, you have to think a little bit more carefully about linking data. So data linkage is the process of bringing together information from two different records that are believed to belong to the same entity based on matching variables. So in the joining examples, we saw sort of employee ID number. And if we link purely on 100% agreement on something like ID number, it's called a deterministic linkage. However, there's also probabilistic linkage, which is that two different rows that agree on several features. If they reach a certain threshold of agreement, then they might be decided to be linked. So we'll look at an example here. Which of these records represents the same person? So we can see, this person has a different zip code, but it's quite close. Got the same birthday, the same name, the same social security number. So probably those are the same people, even though there's a disagreement here. Whereas Robert Jones and Bob Jones, same birthday, there's no agreement on, the sex or the zip. There is the same security number. What about Bill Smith, William Smith? Is this the same? Oof, it's difficult. We have to decide, does this cross a threshold? Is name a shortened version of a full name enough, maybe with the date of birth and zip, it's hard to say. So you will have to decide independently for your project based on your data quality of each of your sources and the research question you're trying to address and the analysis you want to run, what threshold you want to set. So tell me a little bit, if you have joined any data, or actually there's an option to respond with, I don't join data, what kind of methods have you used? Have you used deterministic, probabilistic, something else? Ooh, something else. Interested to know what that is. Do tell me. Good. We've got some variety, including I don't join data. Good. Deterministic seems to be the clear winner, and that's not without reason, because lots of the kinds of data we want to join, we want only absolutely correct matches. But yeah, okay. So lots of people are not joining data. Hopefully. Yeah, okay. Time series as something else. That's fair. That's fair. Propensity score matching. Ooh, guessing that's a probabilistic. Sounds like probabilistic. Okay, good. Good. I'm glad to see that there's some variety of responses here. Because, you know, it's good that people are coming at this workshop from different perspectives. Final point I want to share is that enriching data, which is the process of introducing more data from other internal sources or third-party external data. And it works much like linking data or joining data, but the point is not necessarily to add rows or fill out things, but when reasonable, to add more context to with additional data. So it's to enrich or validate the data. So we can think a little bit less that it's sort of about getting the absolute right answer, but it's about sort of providing a second perspective, a richer source of data that we can look at for double checking our joins, perhaps. Moving on to cleaning, everyone's favorite task, right? Why is data cleaning so important? Because everyone seems to think it's one of the three biggest problems in data. Warehousing DCI survey says it's the #1 problem. And it's generally agreed that quality data beats fancy data mining algorithms. So getting better data, cleaner data is always preferable to getting huge amounts of possibly dodgy data, generally understood that way. And this, again, is about the garbage in, garbage out sort of philosophy, that the better your data starts off, the better your analysis coming out of it. Now, hopefully some of you will be aware that real world data is dirty. It is incomplete or missing, so it's lacking attribute values or certain attributes of interest, or it only contains aggregate data. So, for example, if you had, you know, some data including one column for occupation, where things were just missing, no occupation was listed, or maybe a date, you know, a birth date, where there's just an improbable number of January 1st birthdays, you might suspect that something had gone wrong in the collection process, that perhaps if birthday had not been introduced, it was coerced into listing January 1st or something like that. Likewise, you might get inaccurate or noisy, where there is a value, but you know it's an unreasonable value. So a salary, for example, is listed as -10. That's not a salary. Or there might be inconsistency. So it contains discrepancies between the different columns. So for example, someone lists their age as 42, but their birthday is being in 1997, which is not going to give an age of 42. So these are some of the things you might find depending on how your data was collected or generated. And let's just have a quick look here. For example, this is a lovely dirty data set that we've got to work with. So it's got missing values shown as null or with the word null. And it's got a date column that may or may not be in the format that we want. We can't necessarily be sure that these are all in the proper format. Certainly 2605 is likely day, month, year, but 0803 might be month, day, year, depending on whether Americans or Europeans have entered this state. Couldn't say. Let's see. And we've got, if we know that this is a report generated for Manchester, which makes sense given the city listed here, what's Edinburgh doing in there? That seems like an error. Also, the postcode M88, is that a real postcode? I have my doubts. You know, we've got things like, you know, this kind of thing that you can double check, but it's, you know, you have to be on the lookout for things to double check. And then we've got potential duplicate records. So it's, you know, but they're not exactly matching. So different prices listed, for example, even though they were on the market for the same and the address is the same. So this is the kind of dirty data that you might get. So how do you fix it? Do you throw out the records that have missing values? This could be the right answer depending on how many missing values there are and how big your data set is, but there's a real risk that it creates a bias in your sample, especially because if you have reason to think that records with missing values are not distributed equally among your sample. So for example, if your sample includes people who maybe don't speak English as a native language and your survey was only in English, you are likely to get more missing values for some groups of people than others, for example. So do you just delete the column that has missing values? It's not a good idea, because why were you even asking about that thing if the column is unnecessary? What about replacing missing values with a special value like -99 that you will know looking at this, that was a missing value, but it resembles any other value to data analytics and it will throw off your stuff. What about replacing it with a typical value like a mean or a median or mode, some kind of central tendency value? This is possible. It might distort your distribution, certainly for median, but it could be a good option depending on your data and your research question. What if you do impute a value, like filling in the mean as the replaced value, you should flag it. So you should add an extra column, for example, that shows that this was an imputed value rather than an original value. And that way you can check to make sure that your distribution of imputed values is properly random. What about using data mining techniques that can handle missing values? This is a good option depending on the volume of your data and your research question and the type of data. And also you can partition your records and build multiple models. So some with, some without. You can try and split the data set up in different ways so that the missing values don't throw off the whole model, and you can sort of look at subsets and see if they agree with each other. This is a good option if you have large data sets. It won't be possible if you have small data sets. So here's a question. Imagine we have this sales and customer tracking data for you know, something we're selling. And for whatever reason, you know, October, November, and December of 2014 have gone missing. Oh no, what are we going to do? So how do we deal with this? Let's get your opinions. Do we want to throw out or delete those months? Do we want to replace with a mean, replace with a machine learning prediction, or something else? Yeah. Ooh. People taking a lot of different approaches here. I would say, okay, it's good that we're getting different opinions. And again, as is true for most things when you're working with statistics, there's not necessarily a purely right or wrong answer. As long as you can justify the decision that you've made. I would say it's harder to justify the throwing out or replacing with mean decision, because we know that December is probably going to have a different kind of sales than other months, at least for Christian dominated countries, because there's so many more sales in December. So we might look at replacing with the mean of previous Decembers, or with some kind of machine learning prediction. Yeah, you can get a pattern from previous years to show like what the year to December relationship was, and then try and fill it in from that, or from previous Decembers, or you can even just copy over the previous years, knowing that it will be wrong in some way. So again, none of these is totally perfectly 100% the right answer, but I would agree with the majority of you and say that a machine learning prediction is probably a better answer than just ignoring it or replacing it with a yearly mean. Although a mean of past Decembers might also be a good option. Okay, moving on. How do you handle noisy data? So noisy data is something which there's a lot of variance. There's a lot of apparent randomness. So how do we do it? Generally binning and smoothing and sorting and things like this. So you can sort data and partition into bins of equal width or equal depth. You can smooth though by the means, the median, or the boundaries of the bin. You can do regression. You can cluster. You combine computer and human inspection to detect suspicious values and get some person to manually double check the real outliers. So here's a binning methods. For example, you can sort into order. You could just put them in order and then put them into bins by frequency. So these are equal depth bins. Each of these bins has 4, and then you can smooth those bins by the means or by the boundaries. Technically that should be 15, not 4. So this way you can sort of look at making it into nice, neater packages. This may help with your data depending on what you think is the reason for the noisiness. If you believe it's error in how it was measured or random variance or something like that, then smoothing and binning works. If you think there's a real reason for the noisiness, then you should be exploring the source of that noise rather than trying to minimize it. But this is a way of minimizing noise if we believe the noise is not important. Again, you have to justify why you think the noise is not important. It also reduces the chance of overfitting small data sets. So if your data set is very, very large, binning and smoothing might not be important, but it's something to consider if your data set looks noisy and is maybe not large enough to deal with that noise. Other relevant concepts for cleaning: data scrubbing. So using simple domain knowledge like postcodes and spell checks to detect errors and make corrections. Data auditing. So this is where you analyze the data to discover the rules and relationships to detect violators. So here it's correlation and clustering and outlier detection and things like that. And data validating. So you check the ranges, you look for regular expressions and uniqueness checks and things like that. So some of this comes down to domain knowledge, and you may have to become a bit of an expert, a bit of a detective on what's appropriate, normal, and expected for your data. And this is why data pre-processing can occupy up to 80% of your data work, because there's a lot of critical thinking and creativity involved in checking it rather than just blindly believing whatever shape your data comes to you is the right shape. So you have to be a bit careful. We are moving on to reduction. Why do we want to reduce our data? Isn't more data better? Lots of people say that, and I think they are wrong. The reason why we want to reduce our data sometimes is that we do not want to be working with terabytes or petaflops or whatever it is of data to do something that is maybe not worth that kind of time and computer power and energy resource intensivity. So complex analysis takes a very long time and a lot of computer power to run, and it might just not be worth it for like some basic analysis. So we want to reduce our data. We want to obtain a reduced representation of the data that is smaller in volume, but still gives us the same analytical results. Well, how do we know that? Let's take a look. So we want to reduce redundancy. So data, especially post-joining, but also depending on how the data was generated, you can have a lot of redundancy. So you can have multiple columns that capture the same stuff, or you can have duplicate entries. So these are both, sources of additional volume of data that don't help us answer our question because they're not giving us anything new. This is the kind of redundancy we want to reduce most. So you can do that in a couple of ways. You can remove redundant and irrelevant attributes. You can do principal component analysis or variable clustering, feature engineering. You can also do numerosity reduction, which is essentially sampling, things like that, just to pick out subsets of data. And you can do this multiple times and check to confirm that your samples all agree with each other. And then you can be much more confident that your samples represent the whole in a meaningful way. So let's look at some variable reduction. So correlation. If we know that the variables on the X and the Y axis have a real strong correlation, do we really need to have both of them? Because is it meaningful to double the computer power to analyze these things when there's such a strong correlation? I mean, we can look at all the math here, and you will have access to these slides if you want to go into it. But the like net of this slide is that, like, if we can get away with just having one variable, let's do that and save the computer power for more meaningful things. So, again, like, if they're really strongly positively correlated or really strongly negatively correlated, we probably don't need both. We only need both if there's no correlation, if they're independent. So, I mean, here's a depiction of strongly negative right through to strongly positive. So here we can see, certainly at the very extremes, we definitely don't need both. I would say anything from, maybe 70 or 60% up through 60 or 70 positive. And these you might want to keep both depending on the research question and volume of your data and your other, the access to computer powers. But anything like in the really strongly positive or negative correlations, you can probably get away with just one of the variables. Or you could collapse those two variables. And you can do that. I mean, there's different ways of testing correlation independence. So, all the different kind of traditional statistical correlations that you've done, the chi-squared test, the ANOVAs, these kinds of things. These are ways of testing how strongly correlated they are and whether or not you really need both. So another reduction option is the principal component analysis. So these, if you're familiar with principal component analysis at all, it's a bit of a sort of abstract concept. It's a mathematical transformation, and you sort of sort them. There's a lot with eigenvalues. It gets really esoteric sounding at one point. But okay, hang on, I've got a description here. Principal components are constructed as mathematical transformations of input variables. Each is an uncorrelated linear combination of original input variables. Components can be written as a sum of loadings onto variables. Coefficients of such a linear combination are the eigenvectors of correlation or covariance matrix. So this PCA is by far the most popular dimensionality reduction technique, especially if there are many, many attributes. So correlation is a way of transforming two variables into one. You can just, just pick the one. But principal component analysis collapses lots of variables into fewer. Yeah, exactly. It's really useful as for decreasing, for reducing variables. A small number of principal components can be kept to explain a whole lot of the variation in the original data cloud. But the disadvantage is that it's difficult or impossible to interpret the constructed principal components. So if you're confident on your stats, if you understand principal components, if you understand the data you're working with really well, you use principal component analysis, you get two principal components out the end of it. You kind of just have to trust that there's two underlying components and that they're important, but it's really not, it's not clear what they are or what they mean. So there's numerosity reduction. This is different than principal component analysis. Numerosity reduction has parametric and non-parametric. These don't necessarily have to assume things. They can be simple sampling, clustering histograms. If it's parametric, then you assume that it fits a model. You estimate the model parameters, store only the parameters, and discard the data. So you're probably familiar with a lot of these terms because these are very common statistical functions. People use them a lot, but you may not have thought about using them in the context of reducing super voluminous data. There are other kinds of reduction techniques, like singular value decomposition is one. You can sort of collapse sparse matrices, and that's another kind of way of doing it. There's lots of options. But let's talk about sampling, because sampling is a really popular one, and it's obtaining a small set of samples to represent the whole data set. You can do simple random sampling with replacement, without replacement, or stratified. So stratified is required to approximate the percentage of each class in the overall database before drawing the samples. So it's double checking that your sample matches the representation of the original. So that's a useful way if you believe that there's populations in your data that need to be represented in your sample. Right, that's a lot on reduction. Now transformation, which gets even slightly more abstract than reduction. Apologies for this. There'll be time for questions soon. First, I want to introduce the concept of tidy data. And tidy data is really about shape of data and function of data. So when we were talking about joining the data earlier, we noticed every time if you join two tables, the resulting table is wider than the original. Wide data is less likely to be tidy than long, narrow data. And I'll explain a little bit more about why that is. But it's good to know that wide data is usually quite human readable, whereas long data is very machine readable. And that matters if you're doing analysis. So the features of tidy data are that each observation has its own row, each variable has its own column, and each value has its own cell. So looking at this table of incidents and resolutions in 3 different countries on this date, is it tidy? Does each observation have its own row, each variable have its own column, each value have its own cell? It's time for a quiz. So is it tidy? Yes, no, or Ooh, got some answers. Got one non-committal. I like it. I like the non-committal interaction. That's a dedication to being heard to say very little. Great. I love that those are tied. Oh no. Uncertainty is tying with certainty. I love it. No one thinks it is untidy. I will tell you, it is tidier now than it was. And that is because you'll see type, incidence, and resolutions has been recast into a value for type. And now each observation has its own row. Previously, where both incidents and resolutions were in the same row, that's two different observations in one row. And it's hard to think about this. This is not a concept that most of us are introduced to when we're talking about data. Agreed, this is not as easy for people to read, but it is much better for computers to read. Why does this matter? We'll come to it again in a moment. Yeah, I can show the first untidy data. So you'll see here, incidents and resolutions. This is an observation of how many incidents happened. This is an observation of how many resolutions happened, and they are in the same row. So each observation does not have its own row. Scandalous, I know. Yeah, no problem. Okay, so a little bit about data transformation. A data transformation is a function that maps the entire set of values of a given attribute to a new set of replacement values. This is one kind of data transformation. So relevant methods include normalization and standardization. So we might scale data to fall within a specified range, for example, min-max normalization, z-score normalization, decimal scaling. You're probably familiar with some of these, but we'll just go through them briefly. So we might standardize numeric values. We might change counts into percentages, dates into durations, capture trends with ratios or differences. These are all, or replace categorical variables with appropriate numerical variables. These are all data transformation examples. You're probably familiar with this, but it is worth taking some time to really look at your data and double checking if the way your data is recorded is the most useful way. So year or age, for example, durations, ratios, things like that. Have a think about it. You'll also want to transform variables to bring information out more clearly. So transform using mathematical functions such as logs, reciprocals, or square roots for stretching or squishing. In fact, this came up earlier today in our group. We were talking about if data is really clumpy, do we want to move it to a log format so that it, looks more stretched out and nice and you can see it better than if everything's crammed into this corner? We decided instead to go with a zoom function because we were making interactive plots. But transforming it to a log is a good option if you don't have the option of making interactive plots. Another one is one-hot encoding. And this is to transform a human-readable categorical variable in this feature, in this case, to a machine-readable sort of quasi-binary format. So cat now becomes represented as 1, 0, 0, 0, whereas dog is 0, 1, 0, 0, turtle is 0, 0, 1, 0, fish 0, 0, 0, 1. If we had more kinds of animals, we would need more columns here and more zeros. And there's only one non-zero per row. So the net effect is that you don't necessarily need multiple columns as long as it has the exact same number of digits and only one of them is a 1. The others are zeros. This is a little bit like the tidy data that we looked at earlier. This is much more human readable, but when you're working with like analysis, this is much more machine readable. So you have to think a little bit, not only is data in the right format for you to understand it, but is it the best format to be analyzed by a machine? And those are not necessarily the same. So you might want to transform your variables to work with analysis much more quickly and efficiently, and then transform them back for visualization when you're ready to present them to people. So something to consider. Min-max normalization. I mean, we've probably all done this, but we know that, if everyone in our survey has a minimum and a maximum salary, for example, and income, we don't necessarily want our scales to go from 0 to, 8 million. That wouldn't be helpful. So we might, transform 73,000, for example, into 0.716 based on the min, the max, all of these kinds of things. Likewise, Z-score normalization. So we want to find the mean and the standard deviation, and we want to look at values in relation to a unit of standard deviation. This is another very common statistical normalization function. Probably familiar with it. If not, we can talk afterwards. And decimal scaling. This one's probably the easiest because you just gotta like stick a decimal in there. So, you know, you just find, you know, what's the, how many decimal places do you need to go? In this case, you know, because there's 3 digits, so you divide by 1,000. There you go. That's an easy one. And that means that you can sort of look at things on a scale very easily, which might help with your visualizations, but will almost certainly help with your sort of plotting and your analysis and your conclusions. Here are a couple of resources you might want to look at to know more. You know, a couple of books. Again, these slides will be available on our GitHub repository, which I will show you in just a moment. But for now, some time for questions. Give you a moment to think about it, because I realize I've just thrown a lot of really nerdy sounding stuff at you, starting with Star Wars and ending with like decimal normalization. Pardon me, just so you know, my colleague Louise has shared a link to our GitHub repository for this workshop. You can find, as soon as I update the slides after this session, I mean, there's a version of the slides there now, but I will update them with the results of the Mentimeter interactions after this workshop. And so you will find up-to-date versions there very soon. There's also the Jupyter Notebook versions of the code that I'm going to show you if you want to work through that. Take a few minutes for questions. Here we go. Let's see. Can you say something about data files, weave formats for saving processed data? Yeah, it depends on what software you're working with, obviously. If I usually work in R or Python, and I usually save things in CSV if I can. It's a flat table kind of format. But if you're working with nested data, for example, if you scrape tweets or something like that, you're probably going to get a nested format like JSON files. So it depends on what shape your data, like what kind of data you're working with, and what features it has that you want to work with most closely. Some nested format data might be better to save as multiple tables that have a shared key so that you can pull them together when you need, but you can also just work with a subset of the data if you're going to be working intensely with some of the data and don't want to deal with the fact that there's like 20 columns. You only want 3 columns for most of your work, something like that. Then I would say you can switch to multiple tables and then just work with the one flat table intensely. I don't know if that answered your question. If not, you can ask me again. Oh, hang on. There's would suggest to have a specialized workshop that would go into details on the different stages of pre-processing, as it's the most important part of the processing. Well, you're in luck, because there is a code demonstration after the break in which we do go into the details. I mean, it depends on what details of pre-processing you want to know more about. We will do things like join some tables and do some transformations and check for correlations and things like that. So we do some detailed work that is written in Python. So hopefully that's useful to you. If there's a particular part of this process that you feel is not answered even by the code demonstration part of the workshop, you can reach out and get in touch. We also have computational social science drop-ins the second Tuesday of every month. Find on our UK data service events page, you can find, I don't know if Nadia or Louise can link to our events page or to the next data drop-in. But it's basically an hour in which people show up and ask us questions, and we try and find them help. Yeah, so it's things like people might say, oh, can you recommend a R package that addresses this topic, or what kind of methods would you use to validate this sort of data, something like that. We answer a lot of those questions. Yeah, Nadia has also mentioned that we do have other sort of sessions that we've run. The pre-processing, there's some pre-processing work done in our machine learning series. And also, I think our text mining series, if you're looking at the pre-processing associated with language. You can find those on our UK Data Service YouTube channel, and also the GitHub repository we linked to earlier. There are other repositories in our UK Data Service GitHub repo. Yeah, again, that's Louise has just helpfully linked to the machine learning GitHub repo. So there are also code demos in that repo that you can work through that code as well. So if you might find that those go into more detail on the questions you have. A couple of more minutes for questions to come in, and then we'll take a short break. Let people have a stretch and a cup of tea, or use the loo, that kind of thing. Don't know if anyone else has any more questions just now. If not, I will say thank you. And I will stop sharing. And I will turn off my camera and my mic, and we will be back in, let's say, 2:35, so that it gives you about 6 minutes. Hello, everyone. I'm back a little bit early, but I won't start the second half of the workshop just yet. Do want to remind you that you can ask questions in the chat. I'll keep an eye on the chat, but also my colleagues are in there. They can answer questions if they are able to do so. Let me know if you have had any particular data pre-processing successes or fails, especially if the fails are funny. Share those with us, and we can move on to the next part in just a few minutes. I want to give people enough time to have a good stretch. Sitting down for 2 hours straight is not necessarily good for you. So, well, I'll quit blathering. You know this already, I'm sure. Okay, it's 2:35. So hopefully everyone is back from the break. Just wanted to let you know that here I'm on the GitHub repository for data pre-processing. So that's this session. Under slides, you will see the original when this particular workshop was run in 2021. It was split into 2 parts, and so it did go into more detail on each. So you might find that those slide decks are useful, or the recordings on our YouTube channel. But the slide decks for this session will be under 2023. They will be updated as soon as I can after the workshop. But we will be working in the Jupyter Notebook. So I am running Jupyter Notebooks on my local computer. So you can see here, it's got the local host. There is a binder link that should allow you to work through the code in a virtual environment in your browser. Unfortunately, I've hit the limit on launching that binder notebook for today. So probably if you want to code along with this workshop, you'll need to clone the repository or download the repository. But if you want to just watch for now, you can go back later and interact through the virtual environment in your web browser using the binder link. But for now, I'll just go through the Jupyter Notebook as it's running on my local computer, because I don't need to worry about hitting limits on binder. If you do organize kind of lengthy workshops, goes into detail each topic, sitting with a couple of PGRs, and we need all this in details. Yeah, you're not wrong. Sorry, that was a message to me, but yeah, if you're interested in having more yeah, you can try and clone into Google Colab if you want, if that's interesting for you. You will need to download the CSVs as well, because there's 2 CSVs that I reference. So you can do that. If you want more detail about any of these topics, let me know, get in contact, or come to the computational social science drop-ins. The link to sign up for those was in the chat, further up in the chat. And we can talk in more detail about specifically these topics, or, I can reference maybe some papers that illustrate the different methods, or we can talk about it a little bit more. It depends on how much interest I get, whether we would do another in-depth workshop series, because yeah, some of these are fairly basic concepts that lots of people would know, and they maybe just haven't applied them to this topic yet. But yeah, we can think about it. So to interact with Jupyter Notebook cells, you can either hit run, this little button. So you highlight the cell by clicking in it, and then you hit run at the top, or you can hold down Control and hit enter, which I usually find easier. And in this case, There's a little interactive element. It asks me my name and it says hello to me specifically. Oh, thank you very much. Sorry. Let me just type something into the chat here. There we go. And there's different packages here to install and import NumPy and pandas, which I use throughout this. NumPy and pandas are both very useful for working with numbers and data sets and tables and, you know, vectors and things like that in Jupyter notebooks, well, in Python in general. But so when a cell is running, you'll see there's a little asterisk here, and quite often there'll be like output below the cell. When it finishes running, it'll switch to a number. You can see here, it's got number 1. So this one is still running. Oh, now it's number 2. So that's how you can tell that the code cells have finished running. So now that I've shown you how to interact with the code cells and imported the relevant packages, I'm now going to import the data sets. And if you go back here, you'll see these are stored at the same level as my IPyNB. That's the notebook we're working in, which means I just need to reference them directly. If they were stored, you know, within a folder, I would have to direct the cell to look inside of that folder. But for this one, I just hit Control Enter. It imports these data sets and saves them as these features. So this one, Titanic.csv, is saved as Titan. Titanic-survival CSV is Titan survival, and Titanic features is Titan features. So there's 3 different variables here that are each the contents of these CSV files. So I'm just going to have a look. I'm going to look at survival. So that .head means look at the top 10 rows of this file. Let's have a look. So this is a fairly small file. It's got a row number, a row index. It's got survived as either 0 or 1, and it's got name of the person who either did or did not survive. I don't have the metadata for this, so I don't know whether 0 or 1 means they did or did not survive. That's a bit of a fault. It's something that ideally I would check in the metadata. So here's Titan features. Here we have, you know, the class, name, sex, age, siblings or spouse aboard, parents or children aboard, how much they paid, and where they embarked, I'm assuming. Embarked. Yes, probably where. Again, this is something that you would look in the metadata to find out what these mean exactly. So if there's no number listed after head, it gives you the top 5. If you want a specific number, you have to put that in the brackets. So this is just a little bit about how to interact with Python and Jupyter notebooks. Some of you will already know this. It'll be a hold hat. But for everyone who doesn't already know this, I just want to make sure that you don't feel bewildered. So this one, we're going to look at just some, when we ask for shape, it's sort of like it's saying how many rows and columns are there. So the first one, we know there's 2 real columns plus an index, and it's got 882, 2. This one has 887, 8. So they're different sizes, these 2, even though the names start out being the same. So they go to different lengths. That's interesting. So when we merge the tables based on name, we have to, we know that they won't be a perfect merge because they have different lengths. But we're going to base Titan features and Titan survival using name from each of the tables. And then we'll have a look at merge. So in this case, we see that now there's 9 columns. You can see that here, and there's 882 rows. Now, because I didn't specify what kind of a merge this was, it's given me an inner join. That's considered the basic kind of join. So that means only rows that appear in both are listed in this final merged output, and that we should not expect missing values. So, I mean, that makes sense. 82 rows, now 9 columns. But let's look at maybe the how function within merge. And in this case, we're going to specify how as an outer join. So this means all columns, all rows, and we should expect some missing values. That makes sense. We now have 887 rows and 9 columns. Okay, so does anyone have questions on that so far, on merging? Because there's, well, I'm going to give you impossible to increase the font. Yeah, absolutely. Let me do that. How's that? Hopefully that's better. Apologies, I should have recognized that. I've got quite a big screen, so it might look big to me, but yeah, if you're not working on a screen as big as mine, then it would be a little bit hard to see. Apologies. So because there's 887 rows, and I know that the first one, the inner join, had 882. I know that there are 5 rows with missing values. So I want to inspect the missing values. So I will just say, I'll look from merge 2. This is the larger of the 2 merged sets. Give me all of the rows which have a null value. Here we go. So we don't know if Mr. Francesco Celotti or Emil Christman or Paul Andresen or Herbert Chafee or Bertram Dean survived, because that survived column is full of no value. Okay, so you can try left and right if you want. So I would say to do that, you're going to copy this row. Let's just copy that. You can paste it here and change this to left. Would help if I could spell left, or to right. You can do this now if you want. I'll give you a little bit of time, or you can do it in your own time later. But there is an empty cell here for you to try merging. And if you want to know more about how merge works, there's a link here. This is if you want to write the contents of one of your files to a CSV. So if you want to save the output of this merge, this is merge 1, but you can change that to merge 2, or any of the merges that you create with left or right. You can label those as merge 3 or merge right or merge whatever. You can save those to CSV by using this code here. Okay, do we have any questions on merging or saving to CSV, or for that matter, importing? Give everyone just a little bit of time to try out merge left or merge right if you find that interesting, or to ask a question before we go on to data cleaning. Okay. It looks like there are no questions on merging. So good. I'm going to assume that everyone's very comfortable with merging and we're all happily merging away. So data cleaning, as we know, data in the real world is not neat and tidy and perfect and with no missing values or no inconsistent results the way that data given to us in assignments often is when we're in formal education. In the real world, it's, caused by all kinds of problems, like, maybe it's sensors. If our data includes sensor output, the sensors might malfunction. There might be some kind of power outage that cuts off some data. It's missing some values. It's inconsistent with other data. it's not been entered properly by some data entry process. It's just missing, or, it was changed or damaged at some point. So we talked about these kinds of possible options, like throw it out or delete or replace it with something special, replace it with a mean value, use some kind of data mining, machine learning thing to fill it in with something sensible. But, so there's a lot of options we can do. So we want to check the missing values. So in our original file, we want to, these are the, let's just have a look first. Class, it looks like this is missing 5, age is missing 8. So if we go back up and we look at the original data, Titan features, we can see that age is one column and class, that's probably P class, probably stands for passenger class. Again, something that the metadata should be able to tell us. So we're missing passenger class for 5 rows and age for 8. It's not terrible, given that there's 887 rows in this data set. That's not a huge amount of missing, sort of missing data. Get the quote and count of the unique values of class. But let's just have a look at whether class is well distributed. It is not. You will not be surprised to find that there's more third class. There's more first than second, though. That's interesting. So anyway, these are not super well distributed, but we can fill in the missing values for class with the most common, third. We can assume that probably these missing values are third class because that's the most numerous. It's an assumption. We should definitely clarify why we're doing this. Should we, if we decide to make this decision and fill in all 5 of these as third class, we should clarify why we've made that decision. Likewise, we can do the same for age. The mean age is 29.46. And so we can fill in those missing ages with the mean age, 29.46. I mean, this is a little bit more about how to do this using the method. In this case, we've just done a simple substitution. We found fill empty, like null attributes with mean age, replacing it 1 for 1 rather than adding another column that has the replaced, which we could have done. You can also just remove the rows within NA because there aren't a huge number of them. Probably could have just dropped them. But again, it depends on the kind of analysis you're wanting to run. So let's just check that the missing values. Now we have all zeros in our missing value summary. So we have no more missing values. I mean, that's good in a certain respect. We should definitely make sure that we have described the steps we've taken accurately so that other people can look at what we've done. Let's check the minimum and maximum. Okay, so this suggests that, how many there are in each. So the count, that's sensible. Mean, standard deviation, minimum, interquartile range, maximum. So survived because that's only a 0 and a 1. That's the interquartile range, and min-max doesn't really mean anything. But passenger class, that's categorical. Again, those sort of don't mean that much. Age is more relevant. So the minimum age is 0.42. So there was one, I guess 5-month-old. And the max was 80. There was one 80-year-old passenger. listed in this manifesto. There may have been other passengers. The most siblings or spouses. I'm guessing it was siblings rather than spouses, because if you have 8 spouses, that seems like a lot of work. But that was the maximum number of siblings or spouses. Maximum number of children was 6. Ooh, the maximum fare was 512, and the minimum fare was free. So, okay, so that's just a little bit of description. So understand this is a bit of exploratory analysis. Here's the explanation for the boarding. Cherbourg, Queenstown, Southampton. So all of these make sense for the range, the min and max. So the ages are all positive. You know, the number of spouses, we didn't get like 1,000 or something like that. The fact that we got 6 as the maximum number of children kind of makes sense, with 8 as the maximum number of siblings or spouses. You know, these are approximate. So if some parent has 6 kids, well, maybe there's a bit of an error there. Yeah, no, if some parent has 7 kids and a spouse, then you would get 8 here. And each of those kids would have a maximum of 6. I don't know, maybe no, there's a problem there. Anyway, so there's a little bit of an inconsistency there between sibling spouses and parents' children. Unless someone had a sister and then a husband, a spouse, and 6 kids. So it's possible that makes sense. Anyway, I'll stop thinking out loud. But let's go on. We want to check the noise by making sure that there are only 3 different answers for where they embarked. So here we wanted to make sure that there wasn't, for some reason, some kind of error here. And that's, we get S, C, and Q as the unique results for where they embarked. So that's fine. This is making sense. It does, however, we do want to point out the age and passenger class. We're pointing out these are floats, so they're numbers with a 0 after them. When, you know, maybe we want whole numbers. Certainly for passenger class, there's no half class. You know, it doesn't make sense to be a 1.5 class. So you can change the type of those columns. But we can get info, for example, and it shows that passenger class is a float and age is a float. So we can change that to age as an integer. So now it's listed as just numbers instead of sort of numbers with decimal points after it. So that makes more sense. Likewise, we can do both at once. Remember to assign result to the original variable to keep the change. If you wanted to, this is just showing the result of changing age to an integer. It does not actually change age to an integer in the data. It's only showing what would happen if you changed age to an integer. And you'll notice the difference here is that there is no Titan equals at the beginning of it. What this Titan equals means is that you show age and P class as an integer and then save it as Titan. So if you want to try and change, you can play around with this if you want to try and change them back to floats, or if you want to change anything else. For example, you know, these embarked as an object. It doesn't really make sense to change any of these others to integers, but you could if you wanted, I guess. Play around with it if you want. There's some space there. So let me know, do we have any questions on cleaning, on data types, on noise, on filling missing values. Do we have any questions on this? I'll give you just a few minutes here. Okay, doesn't look like we're getting any questions. So we can move on to data reduction. Again, why reduce data? Well, it's not very important if we have 887 rows in our database. But if we have 8 million rows in our database, then it's much more important to really be using the minimum amount of data that we should be working with, instead of wasting time and processing power and energy to crunch a bunch of numbers that it doesn't do us any good to crunch. This is also important if we know we're working with huge volumes of data, which might totally be reasonable if we're working with fast moving, voluminous, complex data. It makes a lot of sense to reduce the dimensions, remove the redundancies, and sort of subset the data maybe to only work with the parts that we need to. So we talked about some of these methods. So removing redundancies, principal component analysis, clustering, feature engineering, numerosity reduction, and you can do that by sampling histograms clustering. So one way of doing it is to perform dimensionality reduction explorations. So we want to check if there's correlations that make sense if we can toss out some variables and keep only the ones that matter the most, or principal component analysis to see if there's underlying sort of component features that we can collapse multiple variables into. So to do that, we need to extract the numerical attributes first. So I'm going to split the data, keeping just the numerical variables. So we've got age, sibling, spouses, parents, child, fair. So we've taken out the names, for example, where they embarked, that kind of thing. And we're going to check for correlations. Now, we can, if you're keen on math and equations, you can check this equation and make sure that you understand it well. But I think we kind of all get the concept of correlations. So we can know that if they're positively correlated, independent, or negatively correlated, we can do different things. So fortunately, we can just tell Python to find us if there's any correlations. And then we'll check what they are. And, you know, all right, we can look at these numbers and we can see, you know, these sort of things, but maybe it's a little bit easier if we just add some colors. So we visualize the correlation matrix with a color gradient. And this just makes it a little bit easier for us to see. So everything is 100% correlated with itself, of course. So these come out as bright red. The only thing that's even warm is parents, children is correlated with spouse, siblings. So it's obviously that larger families have both more parents and children and also more spouses and siblings. But it's not very strong because most times you'll only get like 2 parents with lots of kids, rather, you know, it's not a perfect correlation there. So there's no clear correlation here. We don't have to drop any of these features, but it's very reasonable to check this. And it's also good by presenting this in a Jupyter notebook. That means anyone who reads our paper and says like, oh, you should have, you know, dropped some variables. These are too strongly correlated. You can just show them, nope, they're not strongly correlated. We don't need to drop them. Would also say, if you don't like this basic sort of correlation exploration, you could use ANOVA chi-squared test. You know, if there's categorical variables, we only looked at numerical. But moving on to principal component analysis. Again, there is an equation make sure you understand it if you're very keen on equations. But A, B, and C, these are the loadings, these are the variables. And, you know, the whole point is to find underlying components that represent what's going on beneath the surface of multiple variables. I would say principal component analysis is affected by scale. So you need to scale the features before applying PCA. To do that, fortunately, we just need to import, this stands for scikit-learn, and it's sort of like a basic statistical sciences package. You'll see it a lot if you're working in Python. So we import the package and build a PCA model of two principal components, transform, fit, and save. And just as easy as that, it's ticking away because it's, even with only 887 rows, it's not a trivial amount of work. So you can see this with this asterisk, it's still ticking away. But it will finish relatively soon. There we go. It's finished. So we have our PCA model and we have saved it. So let's have a look at the explained variance. We get this array showing how much of the variance is explained. We'll transform the results to a data set and have a look at that data set. And 887 rows, 2 columns. And we'll see for each of the original rows, instead of this many, you know, all of those variables, we now only have 2 columns, but there's these sort of meaningless principal component 1 and principal component 2. And they're both, you know, between, you know, they're scaled so that they are all like, you know, a proportional in negative and positive. And we can add the output feature of survived. And we'll have a look at it. So we'll see if survived relates to any of these features, 0, 1, 1. So now we've got the same number of rows, but 3 columns because we've added survived. And you might think, well, what does it matter? Do we care? Yeah, maybe. I mean, if our original question was, can we predict who survived? Then this is a valid exploration to find out whether collapsing some of those other variables into principal components shows us a better way to predict who survived. I'm inclined to think it doesn't seem to. Well, it looks like, no, I can't see any patterns right here, but, you know, maybe a deeper exploration would help. Okay, do we have any questions on reduction? I mean, we didn't go through sampling here, which is another kind of reduction, because with 887 rows, you saw even with 887 rows, this step, creating the PCA and saving it, it took, what, a minute and a half, something like that, not a huge amount of time. So it's not worth sampling our data set to get a smaller sample that would run faster. Any questions on data reduction before I move to transformation? Okay, looks like not. So again, transformation is, you know, using one-hot encoding or standardization or, you know, categorical recoding, these kinds of things. So essentially, it's dummy variables. These are valuable kind of ways to think about it. When you put n minus n dash component equals 2. Okay, that's not a question. I don't know if you, oh, that's how many principal components I'm looking for. So I got principal component 1, principal component 2. So if I wanted multiple, if I had reason to believe that there was multiple, that would have found more but 2. Okay, so hopefully that what is the meaning of component? This is, I mean, that's a fundamental question about what principal component analysis is. Principal components are the underlying features that determine complex relationships between variables. This is more than I can cover in this session, but it's like it's a deeper variable that we can't get to, but that we can see the edges of with the variables that we have. Hang around till the end. We can talk about this more if you want, but I'm going to go on to data transformation for now, and you can ask me more at the end if there's time. So one-hot encoding, very common data transformation. Binary variables are used to replace categorical. You need 1 column for each different category, essentially. So here we use a pandas function called getDummies to transform sex, passenger class, and embark location through one-hot encoding. And you now see there's sex_female, sex_male, passenger class 1, passenger class 2, passenger class 3, etc. And for each of the original columns for sex, which was 0 or 1, we now have both 0 here and 1 here, 1 and 0. So you see how these are transformed into 2. Okay, so it's really simple to do a transformation like one-hot encoding in pandas, in Python, because it's just this one line of code that's just like, get some dummies. There you go. For these original categorical variables, just turn them into one-hot encoding. It's great. And now normalization, likewise, is really straightforward. So we can do min-max, z-score, or normalization by data scaling. So we can split the data set to get just the numerical variables first. So here we go. We can import the relevant packages from, again, scikit-learn. Here we're importing min-max scalar and standardization scalar. So, for the different options that we get. Z-score normalization uses the standard scalar. So this is the one where you find a mean and a standard deviation, and you change all of the original values to their terms of how far away from the mean they are in terms of standard deviations. So there you go, really fast. Transform the results. And then we can have a look. This describes the transformed results. So this is giving you a count, a mean, max, standard deviation, or we can just have a look at the transformed results. So here we go. Instead of the original pairs, we get how far away they are from the mean in terms of standard deviations. Likewise, min-max normalization, quite fast. We build the scalar and then run it. So there we go. And now, because they've gone to min-max, we've got these, the max is 1 because it's transformed. Okay. That is how to do some very fast transformations of data. I'm happy to take questions on data transformation, or in fact, on the rest of this Jupyter notebook or the presentation that preceded it. I can go back up within this notebook. I can go back to the slide deck. Let me know what you need. Or I can just wave my hands and talk, and I can stop sharing screen if you want to see me bigger. Or maybe you're done with this and you're like, I'm out. See ya. There's no need to hang about. If you are done, I will actually stop the recording now.